Okay, so the action potential is how electrical messages are transmitted within a neuron. And an action potential is literally a rapid change in potential difference, that's charge difference, right, across the neuronal membrane, that's going to be, of course, caused by the movement of ions across that membrane. And in order for ions to cross an impermeable phospholipid bilayer, well, they've got to have, specific protein channels that let them pass through, right? And at rest, at the resting potential, at minus 65, minus 70, there are no holes really to let sodium, cross over. There are just those very few ungated, sodium channels. So it turns out that within your neurons, you have a great many gated channels. That means that under certain circumstances, these channels are closed and they do not allow for the passage of sodium. However, under different conditions, these channels shift their shape and they open a hole that lets sodium pass from the outside to the inside. Remember, sodium, if you provide it a pathway, right, it will cross from the outside of that cell to the inside because it's driven by two powerful forces, right? By the concentration gradient force, all that sodium massed outside and very little in, right? Because of the pump and the lack of permeability, right, at rest. And also the electrical force, because you're maintaining a charge difference across that membrane. You have more negatively charged kind of constituents on the inside of the cell, and sodium is a positively charged ion. So if you can open a gated channel, if you can ungate it under certain circumstances, you will, basically initiate a flood of incoming, positively charged sodium into the cell. So the initiation of the action potential, the start of the action potential, the start of that sodium current depends rather dramatically on the presence of these special protein machines that you manufacture, again, based on instructions in your genes. It's a specific kind of machine called the voltage-gated sodium channel. Now, this is a channel that's gated, right? It's a sodium channel, so it's selective for sodium, the passage of sodium. And it's gated, which means under certain circumstances it's closed, right? And under other circumstances it is open and lets sodium pass through. Well, the circumstances under which it is gated or ungated is the voltage, is the charge difference across the membrane. At rest, at a voltage of minus 65 millivolts inside versus out, it's in a particular shape. It's shaped like this, with no hole, so nothing can pass through, right? Well, as you depolarize this particular membrane region, right, you actually start to change the electrical forces on the various charged constituents of this protein. Remember, a protein is made up of charged particles itself, right? It's got lots of charged components, right? And so it gets pulled and tugged in different ways, right, as the charge difference changes. And at a certain charge relationship across that membrane, it actually shifts quite suddenly into another conformation, into another shape, whereby it has a hole that lets sodium go straight through. And during this period, when it's open like this, in this conformation, right, sodium will rush inside. And as sodium goes from the outside of the cell to the inside of the cell, remember, sodium is positively charged, it's going to be changing the polarization, right? It's going to be changing the voltage, the charge relationship across that membrane. In fact, you're bringing a positively charged ion inside the cell through these voltage-gated, and at that point ungated, channels, right? And so you're going to be depolarizing it. And as you depolarize it, further depolarize it, this thing shifts again into a third conformation. It goes one more time, and this conformation, is closed again. It's gated, but it's also not going to open again, until you go back to the resting potential, until you can repolarize it, back to the resting potential. Then it goes and gets sort of cocked and ready to go again, right? So let's walk through this. So at minus 65, the voltage-gated sodium channel is in a shape, a conformation, whereby it is gated and closed. No sodium can pass. If you depolarize the membrane, however, right, to minus 55 millivolts, this is the what's known as the threshold voltage, right? At the threshold voltage, all of a sudden this thing shifts into an open conformation, allowing for the passage of sodium. And sodium, driven by the concentration gradient force and driven by the electrical force, rushes inside. And because sodium is a positively charged ion, it'll further depolarize that membrane region, right? So you'll go from -55 all the way up, it turns to +20, because you got all the sodium now, massed on the inside of that location, right? Well, this changes this shape again. So after 1 millisecond actually of being open, 1/1000th of a second of being open, this thing shifts into a third form, right? Where it is also gated and closed. But this time, even when you go back, even when you repolarize, to -55, for example, it will not open. It will only reopen again if you can repolarize all the way to -65 to the resting potential. Then it goes, and then it's ready to go again.